Alright. So yesterday we talked about Pythagorean identities, and then just let's go ahead and write down these quotient identities. So cosecant of x is, well, it's the reciprocal of what? We talked about this yesterday, 1 over the sine of x. These are called the quotient identities because they're quotients, they're all fractions. The secant of x is 1 over the cosine of x. And if I had designed these, I think I would have made secant go with sine and cosine go with cosecant, but that's not how it is. We talked about this briefly yesterday. Tangent of x is equal to the sine of x over the cosine of x. So if we run into sine x over cosine x, then we can immediately just change it into tangent. Now the angles, the x is kind of taking the place of the angles. The angles would have to be the same in both the sine and the cosine in order to replace it with the tangent. All right, if tangent sine over cosine, the cotangent would be cosine over sine. Because cotangent is the reciprocal of tangent, isn't it? The tangent is the reciprocal of tangent, so cotangent is cosine over sine. I can't remember if we did this yesterday, but just bear with me even if we did. I'm going to talk about this one right here, why that's the case. Sine is equal to opposite over hypotenuse, right? And cosine is equal to adjacent over hypotenuse. So if I turn this into a big fraction and make it sine over cosine, then we would just divide these two fractions. Of course, we're going to have a big old complex fraction there. What do those two smaller fractions have in common? Both being divided by the hypotenuse. So what can we do with those hypotenusi? You can cancel them out. If that doesn't sit well with you, then you can think of it this way. If I multiply by a fancy version of 1, h over h, then multiplication would cancel the division there, multiplication would cancel the division there. Sine over cosine turns out to be opposite over adjacent. And what else do we know that's opposite over adjacent? Tangent. Got it? Excellent. Let's practice a little bit. These are going to be kind of similar to the problems that you're going to see at Excel. Actually, that third one is significantly more difficult than I think you'll run into. So the idea here is we're going to simplify these things using, we've got a couple things that we can use. Yesterday we learned about cofunctions of complementary angles. Somebody remind me what the whole deal with cofunctions of complementary angles was? Cofunctions of complementary angles are equal. Okay. Yep, they are. Can somebody give me an example of two things that would be equal that are cofunctions of complementary angles? Just make something up.
Sin of 30 minus cosine of
The sine of 30 and the cosine of 60. These two things would be equal. Remember yesterday we learned that if we have cofunctions, the cofunction is the version of the function without the co. Like cosine is the cofunction of sine. Cotangent is the cofunction of tangent. All right. Cosecant is the cofunction of secant. So sine and cosine are cofunctions, because they're the exact same thing except one says co and the other one doesn't. Right? So if you have two cofunctions, and inside of those two functions are complementary angles, angles that add up to 90 degrees, and they have to be equal to one another. This is just review. So tangent of 20 would be equal to the cotangent of what? 70. Tangent and cotangent are cofunctions. 20 and 70 are complementary angles. The secant of 10 would be equal to the cosecant of 80. Okay, so we're going to use this along with those fundamental identities that we talked about on that last page. So let's start with this first one here. Now, when I look at this one immediately, I'm thinking Pythagorean identity because I see a couple things being added together that are being squared. Okay, sine squared and sine squared. But this isn't the Pythagorean identity because for the Pythagorean identity, for one, they would have to have the same angle in them. Looking at these, I'm thinking Pythagorean identity. So what's wrong with it is that they don't have the same angle, and also I need a sine squared and a cosine squared. Okay, I would like to use this identity right here, sine squared plus cosine squared. And I could just turn that whole thing into a 1. So what can I do to make that happen? Could I change one of these sines to a cosine? I could. If I do, that means I'm going to have to change the angle as well. Which one would you prefer to change, the first one or the second one? Which one? Second one? All right, so we'll leave the first one alone. And I'm going to change it instead of a sine squared, I'm going to change it to a cosine squared. But then the angle has to change as well. The angle is going to have to change to its complement. And what's the complement of 79? 11. Well, that's convenient. Now they both have the same angle. And we've got sine squared plus cosine squared. And what is sine squared plus cosine squared? 1. So our answer is 0. That was fun. All right, let's do another one. Let's do another one. Now, this one here, not sure exactly what to do first. I could get rid of this fraction, I suppose. We could instead of talking about 1 over the cosine, what can we call that instead? It's the same as 1 over the cosine. Secant. Why don't we start there? Cosecant of 32 minus the secant of 58. 1 over cosine is the same as the secant. And, all right, now they got different angles. So maybe and they're different functions. Maybe we'll change one of them into its cofunction, do the complement. You want to change it first or the second? Doesn't matter. How about the first? We'll change the first one this time. Cosecant can be changed into which function? Secant. Its cofunction is secant. But when we do that, we're going to have to also change our angle into its complement. And the complement of 32 happens to be, it's 58. So secant of 58 minus secant of 58 equals 0. It's also fun. Anybody want to take a guess what the answer on the third one's going to be? 0. 0. Now, when we get to identities, and even in this unit, just lucky guesses aren't going to get you anything. Okay, so you're right. I'll tell you the answer is 0. I'd like to see if you can go through a couple small steps to make it equal to 0. Only changing one thing at a time. Go ahead and do it. See if you can do it. By the way, there's lots of different ways you can get to 0 from this. However, it is important that you only change one thing at a time. Get there? What? Let me see. Here's your steps. Oh, okay. Yeah. Ooh, tricky. Nicely done. Nicely done.
is that?
Where'd you get that one up there?
That's for the identity.
Yeah, but cosine squared plus cosine squared is not 1.
Yeah, but you need to.
Oh, you gotta show that step. I show every step. And we're not doing a whole lot with identities in this unit, but that is going to be very important. When we do identities, those are like proofs. The idea is not to come up with the answer. I already told you the answer was going to be 0. The work that you need to show that you understand this is you need to show one step at a time, and you got to show every single step. You can't skip anything. So a lot of you guys are turning the top of this fraction here into a 1, or you're looking to turn that into a 1, and that's a good strategy. But before we can do that, we're going to need to make it look like sine squared plus cosine squared. So we could transform this cosine squared into a sine squared. Of course, we need the complement of that angle, so that's going to be 70. And then now we got sine squared plus cosine squared with the same angle, so we could go ahead and change that into a 1. And we know that the reciprocal of secant, 1 over secant, is equal to what? Cosine. Instead of 1 over secant 70, let's write it as the cosine of 70, because cosine is 1 over secant. And we're either going to change that cosine 70 into a sine 20 or the sine 20 into a cosine 70. Either way, it doesn't really matter. Let's change this into a sine 20. Cofunction and complementary angle. Okay, you need no fewer than those steps that I've shown there to get full credit on a problem like this on the test. Okay, and when you're doing these problems in your homework, I want you to show those steps as well. Now, that's not the only way to do it. Did anybody turn the cosine 70 into a sine squared 70 up here in the beginning? And then you ended up, well, I guess it wouldn't have mattered if you still ended up with a 1 on the top. Earlier today, I had somebody turn the sine 20 here into 1 over secant, or 1 over cosecant 20. So there's different ways to do it, but you need to show only one step at a time, and you gotta show the whole thing. Any questions on that? Think we can tackle something like this? This is pretty advanced for where we're at right now. The ones you're gonna see in your homework will be significantly simpler, more like the first two. Are we good? Do you guys have any questions at all from 7.1 then? I'll take any homework questions from 7.1. And I'll ask for questions on 7.1 again tomorrow, but then that'll be it. That'll be the only time I spend any time talking about 7.1 in class. How many people started 7.1 yesterday? Everybody finished it? Aside from maybe that stuff that we just did? Cool. All right, well, I'll ask again tomorrow. It's time to move on to 7.2 then. The law of sines. So we've been dealing with and reviewing right triangle trig, SOHCAHTOA. Talked a little bit yesterday about the Pythagorean theorem too. And SOHCAHTOA and the Pythagorean theorem are great tools, but those are kind of geometry level tools. I'm pre-calc now, so we're going to graduate to some tougher tools. Not more difficult, but tough. Tough juggles. The problem with SOHCAHTOA and the Pythagorean theorem is that they only work with right triangles. In pre-calc, we're going to be dealing with triangles that are not right triangles. That would be acute triangles and obtuse triangles as well. So we got to set SOHCAHTOA and the Pythagorean theorem aside and bring in some new tools. And those two tools are going to be the law of sines and the law of cosines. I'm not aware of a law of tangents. We'll always ask about that. So we're going to learn law of sines today and tomorrow, and we'll move on to law of cosines on Friday. And for right now, this first piece isn't the most important thing, but I want to talk about how to recognize when you can use the law of sines. And there's kind of three different situations where you can use the law of sines, and that's AAS, ASA, and SSA. And this should sound familiar to you from geometry. Okay, so it depends on the information that you're given. So the way these problems are going to typically work is you're going to be given information about 3 parts of a triangle. By the way, there's 6 different quantities inside of a triangle. There's 3 side lengths and 3 angle measures, right? So typically you're going to get a problem where they will give you 3 of those pieces, and your job will be to solve for the other 3. So how do you know when you can use the law of sines to do that? And one answer to that is if the information you're giving takes the form of angle, sides. So I'll give you an example of this. For example, if they give us a problem, they tell us that this angle was 30, and this one was 45, and this side was 6. That would be angle, side. Angle, side, angle would be something like this. This one's 30, this one's 45, and this one's 6. You see the difference between angle, side, and angle, side, angle? With angle, side, angle, the side is touching both of the angles that are given, just like it is in the name of it. The S is touching both A's. And then SSA, right? And you didn't actually use SSA in geometry. That was the bad one. SSA means you got an angle. Say this is 40 degrees. And you've got 2 sides, but the angle's not between the 2 sides. So 2 sides in a not included angle. So say this is 10, and this is 30. Doesn't look very 2 scale, but let's try it. You get the idea? So in all three of these cases, we could use the law of sines to solve the triangle. There's another way that you can spot these pretty easily once you've got the triangle sketched anyways. In general, if you're looking at the given information and you can see an angle and the side across from it, so an angle and the side across from it, that means you can use the law of sines, like this one. I know that this side's 30, or that angle's 30, and the side across from it is 6. I have both those pieces of information, I can use the law of sines. Same thing here. I've got a 40 across from a 3, I can use the law of sines. Now this one, the only side we have is a 6, and oh no, I don't know the angle across from it. I guess I can't use the law of sines, right? No, you would find that angle in about 5 seconds, right? What is that angle? You don't even need a calculator for it, right? 105. So if you've got 2 angles, even though I don't have this angle, you can find this angle super fast. So I would say, yeah, definitely law of sines for this. Alrighty? Now, in this section, all the problems you're going to encounter are going to be law of sines problems. You don't need to worry about recognizing whether or not you can use law of sines. However, when I give you a test or a quiz over this stuff, I'm not going to tell you which one of the 2 you should use between law of sines and law of cosines. So just figured I'd reintroduce that. We'll talk about that again after we finish up with law of cosines. We'll talk about identifying which one's the best tool to use. So, all right. Before we get into the actual law of sines, we want to talk about some conventions. Remember, conventions are just rules that kind of the community at large decided upon. Okay, so triangle naming conventions basically says, and you probably don't need to write this down because you're going to be doing this so much that it'll become second nature. I just want to make you aware of it right now. Naming conventions say that typically we're going to use a lowercase letter for our sides, and the sides can be whatever we want them, wherever we want them to be. A lot of times in the problems you're going to get, they won't actually give you a picture. They're just going to say, A equals 6 and C equals 5 and this angle equals this. And you're going to have to draw your own picture. And that kind of freaks people out at first, but you get used to it really quickly. So you'll just draw yourself a generic looking triangle like that, the label A, B, and C wherever you want. If I felt like it, I could put my C over here and my A over here. How was it before? C here and A here, right? If I wanted to, that's fine. It's still perfectly valid. The thing that's really important is that your angle alpha must be across from the side A. Those two things have to be across from one another. Beta has to be opposite from B, and gamma has to be opposite from C. Okay? So just make sure when you're setting up your triangle, you always got alpha across from A, beta across from B, gamma across from C. Note that sometimes some books use capital letters for the angles. They're actually using those letters to represent the vertices. If you remember back in geometry, we always use capital letters for vertices. But they name the angle based on the vertex. So, but I think most of what you're going to see, we're going to be using alpha, beta, and gamma. All right. Without any further hesitation, let's do the law of sines. And that's the law of sines. Kind of a weird looking equation. It's got two equal signs in it. Don't worry, we're never going to solve something that's got two equal signs in it. The law of sines states that the ratio of any angle to its opposite side is the same. The ratio of any angle, the sine of any angle to its opposite side is the same. So if I create a fraction by taking the sine of alpha and putting it over top of A, which would be across from alpha, the value of that fraction is going to be identical to the value of the fraction if I'd done it with B and beta. Or C and gamma. All right. Note that on the top, we're always going to have a sine of an angle. And on the bottom, we're going to have a side. When you first start doing these, double check and make sure that you're putting the correct thing in the correct place. Angles go on the top, sides go on the bottom. Just one more time with our naming convention. If this is A, this would have to be alpha. If this is B, this would have to be beta. If that's C, this has to be gamma. Okay, that's the law of sines. We feeling okay? Want to see how you use it? Yay, let's solve a triangle. So just sketch this. All these words and everything, don't worry too much about them. We're just going to use this to kind of annotate this problem as we go. So sketch that triangle, and we're going to solve it. Now this is a nice one because we are actually provided with a picture. In many cases, you will not be provided with a picture. You'll just be given a list of information. So before we actually get started on this, let's write out what would the information have been had they just given us most of the information. They gave us 3 pieces. What 3 pieces did they give us? They gave us one of the sides. Which side did they give us? A, B, or C? C? It's got to be C by process of elimination, right? Because it's not A and B. So they gave us C was 5. And they gave us a couple of angles. Which angles did they give us? They gave us gamma. Gamma is across from C, so gamma would have to be the angle across from C, which is 95. And they gave us what else? Beta. That's the one across from B. And that was 45. So, in your book, a lot of your problems are just going to look like that. They're not going to give you a picture. They'll just give you a list of values, and you'll have to draw your own picture. So this is our first one. Here's your picture. You're welcome. All right, so our job is to find the 3 missing pieces. And the easiest one's going to be alpha. right? You don't need a calculator even to find alpha, do you? We know that angles have to add up to 180, so we're using up 140 already, so alpha is 40. Are we okay with that? We just gloss over that whole alpha part. It's got to be 40. All right, we're going to find A. If this were a right triangle, if that had been a 90-degree angle instead of a 95-degree angle, I'd be looking to use SOHCAHTOA, but since it's not, we're going to have to use law of sines. So we're going to go ahead and set up an equation using law of sines. And let me show you kind of the framework equation that you're always going to set up when you're doing law of sines. So sine of some angle over some side equals the sine of some other angle over some other side. That's what our equation is going to look like. We're going to have two fractions equal to one another. And I've decided to solve for A first. That was just a random decision. We didn't have to. But I've decided to solve for A. So we're going to want to make sure A appears in one of these fractions someplace. So I'm just going to put in the first one because I feel like it. Doesn't really matter. Should it go on the top or the bottom though? Remember it is a side. Should A go on the top or the bottom? It should go on the bottom. Sides go on the bottom. And what should go on the top of that fraction inside of that sign? It should be 40. It's always the side and the angle opposite it that make up the pair that appears inside one of those fractions. So sine 40 over A is one of our fractions, and now we just need to put some values into that other fraction, and I need to pick another pair. So pick a pair of angle and opposite side that we could plug into that second one. What would be the better choice of the two options? 5 and 95? You don't want to go for 45 and B because why? We have two variables and we can't solve that. So we'll go with the 95 and the 5. Make sure we get the angle on the top, so that's a 95. And the side on the bottom, that's a 5. And there we go, we've set up our equation. I'm just annotating here as we go. All right, next thing we're going to do is cross multiply. So go ahead and cross multiply to get yourself an equation. Oops. Is anybody tempted right now to type 5 times the sine of 40 into their calculator and turn that into a decimal answer? No? That's wonderful. That's wonderful. Hopefully you guys are all being honest with me right now. If you are tempted at all to type 5 times the sine of 40 in your calculator, you need to get over that immediately. Okay? When we do these problems, you're not going to type anything into your calculator until the very last step. Okay? You get the variable by itself and you deal with all the signs and everything else you got in there. Until you get that variable by itself, you do not put anything into your calculator. Okay? Because otherwise you're going to get rounding errors. You're going to run into trouble if you do so. So don't turn this into a number. Just leave it there. How am I going to get that A by itself? We're going to divide it by the sine of 95 on both sides. So we're going to end up with 5 times the sine of 40 over the sine of 95. When we type into our calculator to get a value for A, we're going to type one thing into our calculator. Type that whole big thing in all together. And if you guys could go ahead and do that on your calculators right now and make sure that we all get the same answer. Remember, in this class, unless told otherwise, we'll be rounding to the nearest 1,000. Hooray! We did it. Any questions? What do you think about lot signs so far? Most people usually find this pretty straightforward, and it is. Until we get to the ambiguous case tomorrow. But enjoy it for today, because it's not too bad. Let's write an equation to solve for B. So we'll go back to our kind of templates or framework lot signs equation. Let's write an equation to solve for B. So obviously this time we're going to need to get B in there. B's a side. So what do we want, top or bottom? Bottom. And the angle across from B is 45, so that's going to go inside the sign on the top. Now, for my other fraction, I now have two options because I now have a value for A. Should I use it? No, because it's not exact, is it? We rounded it. You did round it to 3 decimal places, so it's fairly accurate. But we did have to cut off, an infinite number of other decimal places, and that means there's some error in there. So always go back to the most exact values you can when you're solving. I almost just did this. Actually, let's say I did this. Oops. What did I do wrong? I put the side inside the sign, and I put the angle on the bottom. Boy, that's so easy to do. Watch out for that. All right, and then I'm just going to take this in. And if, those of you who know, there's a little shortcut for solving these. Anybody know? Can you just look at this and type something in your calculator and get your final answer?
Yeah.
What do you type out? 5 times the sine of 45 divided by the sine of 95. How many of you guys are aware of that little shortcut? I'm okay with it. As long as you write the equation, I'm okay with you just going straight to the answer after that. B ends up being 3.549 unless I've made a mistake. Does that look right? Cool. Any questions? All right, your turn. You try it. Sketch that on your notes. Solve it up. Let's see what you get. Think. Please correct me if that's not right. That's right. Is it wrong? That's right. How about that one? Let me know if you have questions, and I want to talk about one quick thing before we move on. They're on the class website. There's a huge, there's like 30 slides. So I posted it, but we didn't take them. We just kind of I actually recorded a video. If you can't find it, it's where you would find the assignments, the book pages and stuff. We also had an announcement yesterday that we had an optional thing for the test. Over the weekend, it's going to go on Grable, it's going to get points. Covers both of the last units, on those international expressions. People trying to pull up their grade before the end of the quarter. It's an option. It'll be graded. Very cool. That'll be posted online tomorrow, or sorry, Friday. All right, anybody have any questions? We got it done? Okay. Now, this is going to be a little unscientific, but we've got some time, so I want to talk about this. We're going to do some measuring and some building. And I don't have enough rulers for you. If you've got a ruler, you can get one out. I don't know if any of you have one of those little, well, I guess we don't have agendas anymore. But we're going to do some unscientific rulering, measuring with our fingers. Okay? So like, this would be like 6 fingers wide. Right? It'll be close enough. Okay? So what I would like for you to do is construct a triangle for me that has the following values, okay? I'd like you to try and construct a triangle that has alpha equal to 45. Now, we should all be fairly confident at drawing a 45-degree angle. You guys should have a pretty good idea of what a 45-degree angle looks like, right? Hopefully. All right. We're going to let B equal, let's say, oh, I don't know. How about 4 fingers? B is going to be 4 fingers, or 4 inches if you have one of those inchometers. And side A, you know what? Let's make B 5. This is a little unscientific, so I want to make sure that this works out the way I'm wanting it to. B is going to be 5, A is going to be 2. So could you please do your best to construct for me? Now, keep in mind, this angle and this side have to be across from each other, right? So here's what I would recommend you do first, okay? I would recommend you take your pencil and you just go ahead and, as a dash line, nice light dash line, draw yourself a 45-degree angle. I'm really not doing a very good job of that sheet. Smartboard. Draw yourself. Still failing. Come on. There we go. And yeah, does that look good? 45-degree angle. Do that real quick. Draw yourself a nice 45-degree angle. Dash line, though. Dash line. You can go ahead and label it. Yeah. Yep. I'm here. Always happens to me the extension and the heat on everything right. All right, so that's alpha, right? And then I would recommend that you make, well, the B is going to have to go here or here. Would you agree? It can't be the opposite. It can't be opposite from the angle because the side opposite from the angle is what? That's side A, right? A has to be across from alpha, so B's got to be touching that angle. So use your super scientific finger ruler to measure out 5 fingers.
Can we make it 4 fingers instead?
No.
Because really lost.
No.
4 fingers would be like.
Just like measure 2 and then 3, right? Measure 2 fingers, and then put a little tick mark there, and then measure 3 fingers. There we go. we're trying to build a triangle that has these things, right? So you're using your fingers to measure the length.
Your fingers are in.
I thought that. Oh, I didn't realize you were actually being serious.
What's that?
I realized you were being serious.
Well, I don't have rulers for everybody.
Yeah,
So.
I thought we were just playing.
We're kind of winging it here. That's all right, though.
Yeah.
Don't worry, it's gonna work out. It'll work out.
Alright.
All right, and you could have put the 5 down here too. It doesn't matter, but definitely the 5's got to be touching alpha, right? Because if we follow our triangle conventions, alpha's here. That means A's got to be out here. That means B's either got to be here or maybe down here. I put my B kind of up there.
Okay, even me too.
So I'm going to say that this is my 5 fingers here. This is A. This is A. And then we need to make B. I'm sorry, this is B. B was 5. Now we need to construct A. Now A's got to attach up here at the end of this, and it needs to connect up to the other side of the triangle here that's formed by this angle. And it needs to be 2 units long. And that's what I'm hoping you'll recognize, is that that is just not possible, is it? How can I take something that is this long, it's only 2 units long, how can I take something that's that long and get that to connect up with this thing down here? It's just, it's not gonna, it's gonna like waggle here, right? Stretch it, try it. Nope. Just not gonna make it, right? All right, now what if we made it longer then? Okay, so would you agree that this is impossible? Okay, now this is the ambiguous case, because I have provided you with a value for A, a value for alpha, A, alpha, and B, and that's angle side side. We call it side side angle because otherwise it's called that. Side side angle. So this is the ambiguous case. This is what we're going to talk about tomorrow. Now, what if we change this to and made it a 4 instead? Now, if I measure this out again, this is going to be 4 units long. Now is it going to work? Can I swing this down here and get it to connect? Oh, look, it did.
Is that 4?
Yeah, well, I tried to not move it, but I'm saying that that's 4, right?
Yeah.
And then I'm swinging it down here, and I'm maybe stretched a little bit. But it's definitely going to hit down there someplace, right?
Yeah.
All right, so I've created a triangle now that it would work. But here's the problem. Couldn't I also do that? You see what I'm saying?
Did you say? Yeah, they hit it at 2 spots.
It would hit it in 2 spots.
Yeah.
Which means, in this case, I've got 2 possibilities. I've got 2 possible triangles. One of them smaller than the other one. So this thing's called the ambiguous case. And weird stuff can happen in the ambiguous case. There's kind of 3 possibilities. Either the information you're given is like bogus, like the information I gave you to start off with. It's just not possible to make a triangle with that information. It's just not physically possible to get the ends of those triangles to connect to one another. You've got one arm that's just like hanging out there and can't connect. Sometimes though, I'll give you some information and there are 2 possible triangles. And the third case is sometimes I'll give you some information where there's really only one possible triangle. Okay. So we're going to talk about this tomorrow. You're going to find in your, if you go to start 7.2 homework in Math Excel, I think after the 3rd problem, so I think when you hit problem 4, you're going to start getting into ambiguous case. And you're going to know, because the first question they'll ask you is, how many different triangles are possible from this given information? Okay, when you get to that, go ahead and skip that for right now. We're not going to be able to handle that unless you already know ambiguous case. Okay, but you could get started on the first 3 problems in Math Excel. 7.2. All right. If this didn't make any sense to you, I apologize. I'll do my best to make sure that you get it tomorrow.
Makes it.
Don't worry about